2, 1, you're live.
Thank you. I'm John Cserep, here to present a concept for a near-term colony demonstrator, as I call it. NASA's getting to the point where it's starting to think about what to do after ISS, and a number of ideas have been floated. They are still kind of groping for ideas, not sure where they want to go next in terms of destinations. They are talking about putting some kind of station at L1, such as one sometimes called a gateway. Whatever they commit to, it's likely that they're going to be doing it for a long time to come. And at some point, we've been asking, when do we ever get our turn to get some progress towards our goals of making a spacefaring civilization? An idea from the 50s and 60s is something I'd like to talk to you about today. The idea of a wheel-type station which generates its own gravity by centrifugal force was pretty popular for a time, and fell by the wayside in the 50s and 60s, mostly for, I'd say, relatively valid reasons, but I'm going to propose resurrecting this idea. I think the time has come to come back to this and make such a station, but for completely different reasons than were originally envisioned in the 50s and 60s. So in a previous talk to ISDC, I identified the need for what I call a colony demonstrator, which would be a LEO station of reasonable size, but which would include the key features of a full-sized colony. And since then, I've been thinking about the even harder problem of how to actually get such a thing paid for. Even at this scale, it would be quite expensive, and none of us have any money to spend on such things, so how to get it built has been what I've been looking at since then, and it's become a very, very interesting exercise that resulted in what you're going to see today. So my way of looking at this is that if we want to get some kind of demonstrator built, it has to appeal to the people who have the money but who may not actually care about our goals. So the solution, as I see it, is to make a station that serves as many customers as possible while still meeting our needs for advancing the key technologies. So, based on things I've heard at these conferences over the years, I identified 4 key groups of people who might have money that could be leveraged for this purpose. And they are in order: those interested in propellant depots, which you've heard about at this conference. There's a growing interest in putting these, which are basically rocket fuel gas stations, putting them out in orbit or out near the moon to act as enablers for a wide variety of other missions. Usually these are conceived as strictly single-purpose facilities, but I'm going to propose that they be thought of as more like just the nucleus of what could grow to become a much larger and substantial facility, as I'll show you. Second group, those interested in space hotels. You're aware there are a number of companies working now to bring paying passengers into space. They all intend eventually to take passengers into orbit, or they want to have a destination to take them to. Right now they have some very notional idea about what such a hotel might be like. I'm going to suggest that what they think they need is not what they really need, and what they actually need is something a lot more like what we need, as I will explain. Third group are those interested in going back to the moon in any serious way, especially if it involves people. They could benefit greatly from what I'm just broadly calling risk reduction, which is a deliberately broad term covering both people and their equipment, and it would also involve a great amount of cost reduction, as I'll show. And the fourth group would be those interested in going to Mars, who would benefit in all the same ways for the same reasons. And of course there's some overlap between these two groups, but maybe not as much as most people would guess. The bad news is, of all the people interested in spending money on any of these things, none of them is the least bit interested in the kind of station I'm going to propose. They don't know why they would need it or what good it would do them, but that's exactly what I'm setting out to change. So, in order then, the fuel depots have already received technology investments from both NASA and the DoD, and there are at least a couple of American companies working now to develop this into a potential commercial service that they could offer. And this raises the very intriguing possibility that any space station built around such a depot would be a commercially run outfit, meaning that agencies such as NASA would be simply tenants who would just lease space aboard the station as needed. Okay, space hotels. So these companies are wanting to take people to space. When all this activity began over a decade ago, there's some very vague discussion of what space hotels might be like. If you ask them today, they would probably say that they intend for it to be something like a number of Bigelow inflatable modules connected together in a zero-G station, which would seem to meet the two key things that their customer is going to want from a space visit. One is to enjoy weightlessness, the other for Earth gazing. However, I think they're overlooking the fact that you need gravity to be provided for at least 2 major reasons. One is using the toilet. And if you know anything about how astronauts deal with that in zero-G, you know there's really nothing good about it. And it's one thing to ask a NASA employee, excuse me, an NASA employee to put up with that kind of thing, but for guests paying a whole lot of money for a space vacation, no. Not only no, but hell no. I'm just going to leave it at that. The other main thing you need gravity for is eating. And of course, you can eat without gravity. I'm sure we've all seen videos of astronauts floating around, eating M&Ms and little blobs of water in midair aboard stations, but only up to a limited point is that going to be acceptable. When people are spending that much money, spending several days in space, that's a lot of meals to be served, a lot of food floating around, sticking to walls, getting into things. That's really not going to be acceptable. But this seems to present the space hotel designer with a dilemma. How do you provide both gravity and no gravity in the same facility? But we've already seen the answer, because we all know that a wheel type station has a hub, and the hub is an opportunity to provide a zero-G environment. So in principle, at least, you can sort of have your cake and eat it too, and I'll try to show you how we might do that. So both the Moon and Mars present gravity problems basically involving people and their stuff. We don't know how either one really work over the long periods in these lower gravity environments. To try to address this before making the big commitment to a moon base or a Mars mission, it's been proposed in the past that some kind of spin gravity facility in Leo could be the answer. For instance, at this conference a few years ago, Joseph Carroll proposed this one, what he called an artificial gravity facility in Leo, which in his case would consist of a couple of modules connected by tether, and then they would tumble end over end to provide whatever level of gravity you like. Also, the Space Studies Institute has been focusing lately on what they call a G-Lab. The idea here is a little different. They would include little centrifuges in this station, only little ones though, only able to accommodate lab rats or guinea pigs. Neither one of these concepts seems to have really gotten any traction, and I can well imagine why. They're both dedicated facilities that seem to serve only this one purpose. And I think they have generally the right idea. I think we just need to capture these features in a more versatile station, which can also accommodate a number of other customers with other needs. So in the case of the Lunar Proving Ground, as I call it, this is where we could have the chance to see what the effects are of low G on the human body. And it may not be obvious that this is actually a big cost driver, because determining what the tour of duty is that people can serve on the moon determines how quickly or how frequently you have to rotate the crews back to Earth, which is one of the main expenses of running the base. So until you know how long you can leave them there, you can't say how expensive it will be to operate the base. And so why would anyone commit to a moon base if you can't tell them how much it's going to cost to operate it? As for the equipment, we can test such things under the exact lunar conditions, thereby reducing risks before we do the real thing, and mature what NASA calls technology readiness levels. TRLs are all about environment, and there's simply no way to reproduce the lunar environment on Earth. We can have vacuum chambers, but we can't do anything about the gravity. And so here's the opportunity to reduce those risks and affect the whole way that we design our equipment as well. We can test equipment before it goes to the moon, making a standard thing that any equipment bound for the moon first stops at the Leo station, goes through checkout before proceeding. So that reduces our risk greatly there. But it also reduces the engineering costs of developing the equipment in the first place, because if you know that the equipment is going to stop there first and be checked out by someone, then you don't have to try to design in super duper reliable systems with all their redundancy and exotic materials and so forth. Those are the big cost drivers. You frankly can kind of relax and have something more reasonable that has more reasonable cost. You can probably all think of a lot of space missions that have failed or been compromised in the past because of some stupid little thing that went wrong. A little latch that didn't work, a spring, a switch didn't work, or something didn't want to unfold correctly. A lot of missions that would have been saved if there simply had been somebody on the scene who could have, frankly, given the thing a swift kick to allow it to proceed. Well, in this case, we'll have that person there, and knowing that you're going to have that person there means you don't have to try to make the thing super reliable. So, now, I'll do you one better. If you know that a person's going to be there to help with it, then maybe you don't have to design it to try to do so much for itself in the first place. Maybe it doesn't have to try to unfold its own antennas and solar arrays. Since that's a one-time operation, why not just have the station crew do that for it? Now you don't even have to design in the actuators, the springs, the motors, and so forth. So how much more did you just save there on your upfront costs and your operations cost? And I can go further. In the interest of time, I'm not going to speak to all of these, but there are just a whole host of ways to reduce both the costs and the risks of equipment going to the moon. And this should result in a dramatic reduction in the cost of the lunar operations. This is how you make moon operations affordable. When it comes to Mars, all the same things apply for all the same reasons. In fact, they probably apply, in a sense, even more because it costs more to go to Mars, and therefore there's more at stake. Or as someone put it to me, the price of failure is even higher. And therefore the risk tolerance is probably lower. So all that stuff I just said about the moon probably kind of goes double for Mars. Mars also has the unique need to take care of return samples. We want to bring back samples from Mars, and there's a chance that they might have microbial life in them, not just fossil life, but maybe living life. And nobody wants to risk back contaminating the Earth, and so the idea has been that we'll just bring them back as far as the International Space Station, use that as an isolation lab, and just study them there. Well, that idea seems to be increasingly implausible. The station's getting pretty old, and at the rate we're going, by the time we ever get some doggone samples back from Mars, it's unlikely the station is still going to be available to be used. And even if it is, it's really not all that great an environment for studying such samples. If you think about it, zero-G environment to study soil and dust and that kind of thing, really? I mean, if it's all we have, I guess we'll make do, but surely we would prefer to have a much more suitable type of station before bringing back such samples. And also, I'm going to assume that we would get serious about sending people to the moon before we would, or back to the moon, before we go on to Mars. And the concept you're going to see evolves in a way that reflects that assumption. So, if you gather together all those requirements from the previous slides, it adds up to this whole boatload of requirements. And the most important one, however, is this last one. This is about reducing the risk for our long-term goals. That's the only thing that really matters to me. I'm going to keep my eye on that ball. All the other things are not really the reasons to make this station. They're more like the excuses, just the ways to get it funded. But that last one is the one I'm really after. Okay, then let's plunge right into it. Then let's start with creating it. The fuel depot. There are a number of configurations of these things which have been proposed, some of which are spinning facilities. And since we know that's where we're ultimately headed, let's start with one in that kind of configuration. And I'm going to suggest notionally some spherical tanks arranged in a ring type configuration and shrouded by a mirrored housing to keep the sunlight off of them. And you see right here one of the limitations of the software that I use. It's Google's SketchUp software I use to make these. And it doesn't do true ray tracing, and so as a result, I can't show reflections in the mirrors. So you do have to use a little bit of imagination as you view these. So even here, we're already starting to do some risk reduction for the colonies because this kind of funny shaped mirror, which is called a frustum shape, is a feature of most space colony designs I think I've ever seen. And it's kind of an awkward shape to build in space, and so if it turns out to be tricky, here's our chance to find that out and learn how to deal with it. Now the tanks can be spinning, but the spacecraft which dock to it obviously need a stationary point. So there's where you have the hub of the wheel, and up top is where they would dock. And in between, you have this little connection point, what I call the spin interface, which is something usually taken for granted in wheel-type concepts, many of which have a similar arrangement. There's not usually much detail about this, and I'm a little concerned about it. It's not going to be trivial, although I haven't identified any showstoppers. However, I'm just concerned enough about it that I don't want any more than necessary, so I'm going to have just one in the whole station. So from this point on, anything that wants to be part of the stationary part of the station will have to be added above that. Everything below it will be rotating. Now, there's more opportunities for risk reduction even at this early point, because one of the things identified back in the day in the 50s and 60s was that when you have a wheel station and people and equipment move around it, the center of gravity is going to shift, and it could result in a wobbling kind of motion, which would probably be bad. Their proposed solution back then was to use a series of ballast tanks around the wheel, which would have water in them, and the idea would be that you could pump water from one tank to another in order to redistribute the weight as needed. Well, what have we got here? We've got a series of tanks that hold liquid fuel in a ring, and we can practice doing exactly the same thing to show that we can keep this thing balanced as the mass changes, as the fuel comes and goes. And also it might be what I call spin balancing. And there's also the matter of attitude control of a spinning object. That might be tricky. It's likely to be tricky, but this gives us an opportunity to get practice and reduce those risks on a small system that's unmanned and represents a modest investment before we commit to the much bigger station. Let's see. And so it looks something like this. I also want to point out a number of these objects that you're going to see I did not create myself. The spacecraft you see here, I got from an online database. Users of this software can create something, upload it, and make it available to others to download for free. That's where I got these spacecraft and a number of space station modules you're going to see, the rovers and the landers, the people and the astronauts, and most of the furnishings in the station. So I don't want to take credit for other people's work. Okay, well, the zero-G lab, as I mentioned before, it's important NASA understand that if you commit to a ring-type station, it doesn't mean that you forego the opportunity to do zero-G research, because in principle you can do that in the hub. And so rather than include such a thing, I started thinking about what a lab might need to be, and it doesn't particularly advance our goals, however, so I wasn't all that enthusiastic about making some kind of laboratory that I frankly don't really care about. So my conclusion was that we actually don't need to make a lab of our own. All we really need to do is provide a place where other people can bring their labs of the kind that they've already built for the ISS, or the kind we expect to have in the future, like the inflatables, and simply give them a place to hook up to this station, meaning that all we have to add is this little piece here. And then they can come and go over the years as they like. Okay, so the next piece. This is where the guests of the hotel would be able to enjoy zero-G along with Earth viewing at the same time. So the stateroom tower is the next piece, which gets added obviously on the hub. So this is what I came up with. This is a way where you see the outer wall is completely transparent. So that's a thick plexiglass wall, thick enough to provide radiation shielding. And this is one room defined right here. And then another one next to it, and third one beside it, and then three more on another level below them. There's an interconnecting corridor, as you see. And so that gives you 6 rooms altogether. Figure 2 people per room on average, about 12 residents at the hotel at a time. That seemed about right for a first generation hotel. I don't really know how to furnish a zero-G room, so I just threw in a queen size bed there in one of them so you can get an idea of the size of it. Another thing about the Earth viewing business is that it's all very good as long as you have the Earth in front of you, but at other times you might have the sun in front of you, and that very bright sun streaming through those big windows I think would not be enjoyed by the guests, especially if they're trying to sleep. So my conclusion is that hotel rooms are going to have to be kept facing away from the sun, always, which means that the hub is not only not rotating, but it's also being kept in a fixed orientation with respect to the sun at all times. As a result, because these rooms are facing away from the sun, then the backside is facing into the sun all the time, and so that seemed like the logical place to put the solar collectors. And so this is a notional depiction of a solar dynamic power generation system, where those are parabolic mirrors, also called a solar thermal system. This is lacking some components. I'm still learning about what these include. Most notably, I'm missing the radiators. I just didn't feel like I knew enough about them to even guess how big they would need to be or in what configuration. If any of you have a suggestion you'd like to offer, I'd be happy to add them. For now, I'm just going to acknowledge that they're missing. And so it looks something like this. Okay, time to get serious about building the wheel itself. So the next launch brings up an extension of the hub on the bottom there, and packed inside would be all the piece parts you need to build out the spokes, along with at least a couple of robots to do the construction. I say robots, they would probably actually be teleoperated. And I don't know too much about the specifics of them, but I'm getting the feeling that they might be about the size and dexterity of the robots from the movie Silent Running, if you recall Huey, Dewey, and Louie. Imagine something about like that, but with the ability to operate in zero-G also. Okay, but what about building the wheel itself? Now this becomes interesting. I looked at every wheel concept I could find, both the serious proposals and the science fictional ones, and very few of them really talk about how to actually get the wheel built. And all of those that did, I didn't really like anything that I found. And I'm also familiar, as I'm sure you are, the idea of making a wheel out of a series of cylinders linked end to end, kind of like linked sausages, that allows you to set up these prefabricated sections and make it as easy as possible. But nobody thinks we're ever going to build a city in space with that kind of approach. Little prefab modules. We're surely going to need to do true construction to make a city. And I would submit that we've never done real construction in space up to this point. I contend that we've only done mere assembly of things. Like when we envisioned our International Space Station, we kind of broke it down into the biggest pieces we could that would still fit within the space shuttle cargo bay. And we worked on them down here on Earth, and worked, a lot of years, put a lot of effort into them. And then when we got them into space, we wanted to do as little additional work as possible to get them into position and just hook up a few connectors and call it good. Well, that's just about the opposite of real construction. Down here on Earth, we use extremely simple building blocks. We use a whole bunch of them, and we put them together in very complex ways. If we're ever going to have a city in space, we're surely going to have to do something a lot more like that. And since the purpose of this station is to demonstrate things and reduce risks, now's the opportunity to begin learning to do that. So I took kind of a clean sheet approach, and the way I looked at it is to build a wheel. Well, a wheel is kind of an odd shape, but it's at least a symmetrical shape. So my thought was that if you imagine the wheel you want to build, and imagine if you took just a thin slice out of the wheel itself of just a couple degrees, it would be a slightly wedge-shaped thin slice representing the cross-section of the wheel you want to build. In my case, I arbitrarily chose a wheel that would be a square cross-section of 3 decks high. That's similar to the one in the movie 2001, and it turned out to be a pretty good choice, I think. And so my thought was that if you could figure out how to build just that slice in 0G using robots, then after you've done that, you could build another slice right on top of the first one, and then another, and then another, and continue in that fashion all the way around until you've got yourself a wheel. So that reduces the problem of how to build a wheel to just how to build a slice, which suddenly sounds a lot more manageable. And to do that, in a previous talk, I proposed something very notional for doing this, a construction array populated with a number of subsystems I won't discuss here in detail, but the key thing is that it reflects the size and shape of the thing you want it to build, and it's populated with a lot of little robots. These are nothing like the robots we have in space today. These are very simple robots like you might find in a factory, and they would do simple tasks in a very repetitive way. So some of them might simply hold the piece parts in place, some would kind of weld them together, others might just shuttle them around on the array. And they're also attached to this little mobility track which allows them to roll around and move without having to float off into space. My philosophy is that nothing ever goes floating during the construction process. Everything is always held securely by something else. And I haven't attempted to model this whole system in 3D, but imagine that something like this is brought up on the next launch and moved out to the end of one of the spokes, and then you start feeding it piece parts, and it starts building the wheel in cross-section as you see here. And once the wheel's spinning, down is going to be basically outward, so you understand why the decks are oriented the way they are. So that's the lower deck, the mid deck, and the upper deck toward the center. And it continues in that fashion, building the wheel until you have it completed like this. Now the green stuff you see in the foreground is algae and water behind some transparent panels facing outward towards the sun, and its job is to be part of the closed life support system to refresh the air through photosynthesis, much as we do here on Earth. This is another idea that I've read many times, but I've never once seen anyone depict how to actually incorporate such a feature into a wheel station. And I think we do this too often. I want to tell people, I think we do too much, we take things for granted too much. It's a little too easy to say, well, we'll solve this problem with this solution and that problem with that solution. Until you try to combine these things into a complete system, you really have no idea what any ideas will really work. Because it's only when you try to bring them together that you start noticing where things get in each other's way. And then you start having to make trade-offs, and that forces you to decide what your priorities are. And in the end, you can't use the ideal solution to every problem. They just don't work together. But if you can work it and kind of massage the systems and bring them together into a complete integrated concept, you wind up with something I think is a lot more credible and a lot more useful to our community. I wouldn't claim to have completely achieved that yet, but I'm trying to at least take a stab at it in hopes of showing the value of doing so and inspiring others to do more of the same. In fact, I would say that's one of the main benefits I got out of this whole exercise. I just feel like I understand space wheel stations a lot better now, and because there are a lot of things along the way I just had to discover for myself. But anyway, back to the wheel. On the left there you see a part of the wheel where you can tell there's a floor, but there are no walls or ceiling enclosing it. This is the proving ground area. Equipment to be tested gets placed there. The whole wheel spins to provide lunar gravity, and obviously it's exposed to the vacuum the whole time. And using a series of mirrors, we can also subject it to full solar loading, together creating an extremely high fidelity simulated lunar environment, totally impossible to make on Earth, and able to accommodate large equipment for extended periods. On the other side of the wheel, you see another one just like it, for reasons of balance. And so I call these the outdoor areas, and the rest is the indoor areas. And in between are a couple of hangars, which are like big garage airlocks, where you can take the equipment being tested, wheel it in there, seal it up, pressurize it, and then the crew can work on the equipment in a shirt sleeve environment to make any modifications necessary. And then when they're done, they wheel it back out to resume testing. More about that shortly. As for the mirrors, you have to make some assumptions about how the thing is oriented with respect to the sun. So here I'm assuming that the spin axis is vertical and the edge is toward the sun and the Earth, as you see here. And in that orientation, to get sunlight to the station, or here if we're looking at a cross section down here, you can see the algae panels on the outside face toward the sun from left here. And so they can receive sunlight directly, but everything else has to receive it indirectly. And that's done with a couple of mirrors working in conjunction. One is a big angular shaped mirror placed above the spin axis of the station at a 45-degree angle, as you see here. And it works in conjunction with a second set of mirrors down here, also set at 45 degrees. And they go all the way around the inside of the station and therefore form that frustum shape that I referred to earlier. And the idea is that the two work in conjunction. Sunlight coming from the left bounces off one, then the other, and into the inner rim of the wheel. And it does that all the way around. And so the inner wheel, or the inner rim, would be transparent, acting as a skylight to allow that sunlight into the upper deck. And so that's where we would grow the food. That's another part of the life support. This is basically the same configuration as a NASA's own space colony concept from the 70s. You see with the upper mirror, the lower mirrors, and the skylight on the inner rim. So here's our lower mirror, and it looks like that. And the upper mirror is put on a mast to make sure it stays in place. You can see it more clearly here. And I've also got some cables on there to allow you to adjust the tilt if needed. So what would it be like to be inside this kind of strange curved indoor section? Here we're looking at a piece of the indoor arc with the end wall removed. And now I'm going to actually take you into the model. We're going to go into Google SketchUp, and I'm going to show you what it'd be like to be in there. Here we're looking at a section of 15 degrees of the indoor arc, and starting with the outer panels where the algae is, which is where the air gets blown through and refreshed. I have more details about this than I'm going to discuss today in the interest of time, but if you have an interest, I can tell you more about it later. The lower deck, I threw some furniture in here just to give you an idea of the scale. I haven't attempted to outfit the entire interior, mind you. And in particular, this is missing the ladders and stairs, which you would also have for moving between decks. And middle deck, much like first, and then probably the most interesting deck, most interesting one, upstairs, where the food is grown under the skylight. I was only able to find one kind of plant to use here, but imagine a variety of crops are being grown here hydroponically under the skylight. And in addition to providing food, they're also helping to refresh the air. I wanted the crew to have more than just a vegetarian diet, however, and as others have suggested, I've concluded that the best way to introduce other kinds of foods would actually be with aquatic species. And so on the other side of the deck, I've got a representation of my aquaculture system with a series of interconnected tanks, which are meant to represent a complete aquatic food chain of either freshwater or marine species. And the idea is that starting with the algae growing under the skylight, basically little things get fed to bigger things and bigger, until you wind up with something in this last tank, which is edible to the crew. After it's harvested, the leftovers and other wastes are recycled. They're sterilized, broken down, and sent back into the system as nutrients to support the growth of more algae. And you do something similar on the other side with the plants. I don't expect that this is actually going to provide all the food the crew needs by any means, especially not at first. We frankly don't know how any of these species are really going to do under lower gravity conditions, and this is our opportunity to find out. So that's the main value here, at least for the first year or two.